Hi everyone. We have just now worked out a two-dimensional moment problem. You know how to calculate moment now. Moment is equal to force times distance. Moment of a force is a tendency of that force to rotate an object about an axis. So in order to calculate moment, you figure out the distance, which is actually a perpendicular distance, and you multiply that distance by your force. All right? So calculating moment in 2D is easy. But in real life, you are going to deal with forces in 3D. If you think about many objects that we see in our everyday life, such as a transmission tower that is secured by many cables, you are dealing with three-dimensional force. And if you are dealing with three-dimensional force, you are also going to deal with three-dimensional moment. This means you are going to have moment or components of moment along x, y, and z axis. In theory, though, moment in 3D means you have to calculate still the perpendicular distance from an axis to the force. But in reality, it is a lot harder to visualize, sketch, and calculate. So we will use vector algebra. You're all experts in vector algebra, so we are going to use vectors in calculating moments. Now, I want to recall your attention to something what we have done several sessions ago, in which we talked about vector addition, vector subtraction. We also talked about multiplying a vector by a scalar. Now, you remember, when you multiply a vector by a scalar, the length or the magnitude of the vector will change, but the direction remains the same. At that time, you might have had a question. Can we multiply a vector by another vector? Right? That's an interesting question. We didn't talk about it. Well, it turns out you can, and there are two possibilities. You can take two vectors, cross one vector by another vector. You could say vector A cross vector B. That's one possibility. Another possibility is instead of crossing, you can dot. That's known as a dot product. So multiplying vector implies two scenarios. A vector product, also known as a cross product, scalar product, known as a dot product. Let's talk about vector product for a minute. What does that mean? That means you are dealing with two vectors and you are crossing them. In case of moment, we are actually dealing with two vectors. One is the distance. All right, I'm going to call that as a position vector. And then we are also going to deal with force, which is a force vector. It turns out, vector product that you have been studying in math classes all along is actually nothing but moment. Moment is the real application of vector products. So let's take a look at how we can use vector product in solving moment problems, especially three-dimensional moment problems, because it makes your life easier. So let's take a few minutes, solve an example problem, review vector product, and complete our discussion on moments. Hello everyone. Let's talk about vector product. Many times this word has come up, and you have seen this in previous math classes. And you know, vector product means you are dealing with two vectors. For example, I have, say, a vector P, and let's say I have vector Q. And vector product is, I am finding the product of these vectors, or more specifically, if you want to be saying it clearly, I would call it a cross product. So I'm going to say P, vector P cross vector Q. All right? And from your math classes, you know, when you cross one vector with another vector, the resultant is going to be a vector as well, and I'm going to call it R. Now, what that means is the resultant is a vector which has got a magnitude and a direction. The magnitude of this vector is going to be, so P cross Q, if I want the magnitude of that, from math class, you know, it is going to be the magnitude of vector P times magnitude of vector Q times sine theta. What is a sine theta? That's the angle between these two vectors. So if you want to see this visually, here is vector P, say here is vector Q, this is the angle theta between them, and when you cross them, the resultant vector is going to follow the right-hand rule, meaning, let me put the vector as a vector here, that's a vector P, this is vector Q, and when I cross them, the resultant is going to be defined by the right-hand rule. That means if I take my palm, put it along the first vector P, and curl it towards the next vector, my thumb is pointing the direction of the resulting vector, positive side, right? So that vector in this case is going to be R. So this vector R is going to be perpendicular to the plane containing these vectors, perpendicular, all right? So that's a resultant vector. So the direction of the resulting vector is perpendicular to vector P and vector Q. And the magnitude is going to be equal to this. All right? Now, I would like you to explain this in the context of a unit vector. All of you know we assign a unit vector, meaning the magnitude of that vector is going to be equal to 1 along each axis x, y, and z. So, if I have an axis, x-axis, y-axis, and if I have a unit vector defined along x, which is I, a unit vector which is defined along j, that means I can cross now two vectors. Let's cross I and j. I cross j. And by definition, you will see it's the magnitude of I, magnitude of j, times the angle sine 90 degree, right? It's 90 degree. And if I did that, magnitude of I and magnitude of j is 1 and 1, so multiply 1 multiply by 1 gives nothing. And sine 90 is equal to 1. So the magnitude of resulting vector ij is equal to having a magnitude of 1, right? The magnitude of this vector is going to be 1. So that means the resultant vector will have a value, magnitude 1, which indicates it's probably a unit vector, and it is going to be along the direction perpendicular to x and y, and you know that would be your z. So the resulting vector is going to be k. So I cross j is equal to k, a unit vector along z-axis, and it is going to be equal to 1. All right, so that's a basic vector product. All right. Now, just to conclude this discussion, what if I cross I with I? Well, you should know I cross I, the angle between them is 0, and therefore that's going to be equal to 0. What happens if I cross j with I? Well, that means I'm crossing j with I. That means the magnitude is going to be still 1. But if I use the right-hand rule to find the resulting vector, it is not going to be along positive z. It is going to be along positive or negative z, meaning it is going to be negative k. So, what is a vector product? Well, crossing two vectors. And the result is another vector. And the magnitude of the vector is going to be equal to the product of vector times the angle between them, sine angle between them. And the direction is going to be defined by the right-hand rule. You did all this in your math class. But in the context of engineering, P and Q are two vectors that are more meaningful to us. One of them is going to be the force vector. Another one is going to be the position vector. So, how can we apply this for calculating moment? And how can we use this in solving 3D problems is what we are going to look at it. But to complete the discussion, I'm going to draw or show the vector product in the context of a moment. All right? So if I have a force applied here, and I am calculating moment about this point, this is my force vector, this is my position vector. Notice how I'm showing the position vector here. This is my position vector. I'm going to call it R. All right? And that's my force vector. So if I want to use the vector algebra, instead of using just perpendicular distance, I'm going to say I'm going to cross these two vectors. And remember, moment vector is going to be equal to R cross F. So from now onwards, I want you to remember, when we apply vector algebra, moment vector is a cross product of R, which is a position vector. All right, please remember that, position vector, and that's your force vector. But you also realize a position vector R can be written in its component form like this, right? Similarly, force vector can also be written in its component form using Cartesian vector format. And I'm right now doing this in 2D. For 3D, you will have an additional component. So R cross F means you are going to dot these two expressions. I'm sorry, you are going to cross these two expressions, right? I am not going to spend time doing all of these calculations because it's all well defined in books. All right? So you are going to cross these. So each of these components, you are going to use your foil to cross it. And when I crosses with I, you are going to get K. When J crosses with I, you are going to get negative K. And when J crosses with J, I'm sorry, I might have made a mistake here, but you know the vector algebra. So I cross I, angle is 0. All right, so it won't give a unit vector, it will give you a 0 vector. But I cross J would give you K, and so on. All right? Now, you can write this expression and calculate, but if you recall your linear algebra, there's an easier way to do that. For those who forgot, I'm going to just give you that expression. When you have to cross two vectors for calculating moment, you can express this using the determinant of a matrix form where you have I, J, K, and then you have Rx, Ry, Rz, meaning these are all the components of position vector in 3D. And then the third row will be the components of force vector. So this is calculating vector or moment in three-dimensional form, and this form is very useful and very effective because you know how to calculate the determinant of this matrix or the determinant of this matrix, right? And if you can do that, you can actually calculate the moment very easily. And this is very effective and very useful in solving three-dimensional problems. So any times I recommend you solve 3D problems dealing with moment, you would like to use this format. In two-dimensional approach, you could use this, or if you are comfortable doing the conventional way, the way I did in the first two examples, you could do that. But 3D problems, I suggest use this approach because this will help you in getting the correct answers because it is rigorous, basic math involving algebra, vector algebra, and you can't go wrong. The key here is to formulate the problem correctly, finding the components of your position vector and finding the components of your force vector. I hope you understand vector product, and now we will move on to solving a three-dimensional problem using vector products. All right, let's take a look at moment of a force in 3D and use the math behind vector product to solve this problem. The key for solving problems like this is to make sure you formulate the problem correct because the solution process itself is very easy. It is basically solving or finding the determinant of a matrix. And that's something you can do that using your calculator, and you are allowed to keep those tools. So focus on formulating the problem. So let's take a look at this one. Here is a problem from Beer and Johnston. A 200 Newton force is applied as shown to the bracket ABC, a common problem that you encounter in our everyday life. You use these brackets for mounting doors, mounting different devices, and the force is applied. It's in 3 dimension, as you can see. And we want to find the moment of this force about point A. In this particular case, they already gave you a coordinate system, x, y, z, with origin being at point B. So the first thing what you have to do is to make sure you write your force and the position vector in Cartesian vector format. So first identify your force. The force is right here. That's your force. And you do know the magnitude of this force, 200 Newton, but you want to write this force in Cartesian vector form. How do you do that? You need x component, y component, and z component. And if you write this, it should look something like this, correct? But you need the components. Let's try to look at the x component. The way this problem is given, this force is in a plane, I would say YZ plane. It is not in anywhere x, and therefore there is no x component, and therefore it is going to be 0I. You don't have to write 0, but I want to make sure you understand there is no x component, so 0I. Where is the y component? Well, you can see the y component right here. This is your y component. And this is 30 degree. So you can actually visualize a right triangle here. And if you visualize the right triangle, this would be your y. This is your y, parallel to the y. And that would be a cosine 30. So it is going to be, and by the way, the direction of this force is going to be negative because it is going in the negative y direction. So it's going to be negative 200 cosine 30 degree. I hope you understand that. That's your J. In other words, I'm taking this force, projecting into the y component, and since it is pointing down, it is negative, and this component is going to be cosine 30. And that leaves now finally for the z component, and the z component, as you can see, is along here, and it is going this way, so it's positive z, so plus 200, and it is this component. I can either say cosine 60 or sine 30. They are the same, but I'm going to use this angle, so it's going to be cosine 60k. All right. So what I have done is writing this force in Cartesian vector format. Minus 200 cosine 30j plus 200 cosine 60k. Make sure you understand how to do this. This is a critical step. Once you have formulated force F, we need the angle. We need the position vector. And the position vector is from A to C. Why? Because they said calculate the moment of a force about A, so you draw the position vector from here to here. This may be the easiest way to do it. All right? So that's my position vector. Now I need to write this vector in Cartesian vector form, meaning I want the x, y, z components. In other words, I want to do this. Exactly like what I did with the force. But I need to find these components, x, y, z components, and the easiest way to do that would be to find the coordinates of A, which in this case, coordinate of A is 0, x coordinate is 0, y coordinate is negative 50, and the z coordinate is x is 0, y is negative 50, and the z is 0, right? Similarly, I look at the point C, x coordinate is 60 millimeter, y coordinate is going to be up here, 25 millimeter, and the z coordinate is 0. So I know the coordinate of z, I know the coordinate of A, so I can actually calculate the position vector r, which would be equal to C to A 60 I 25 minus 50 plus 75 J plus 0 K. Now this is a position vector, this is in millimeter, and if you want to convert that to the meter, because we want to calculate the units Newton meters, I believe this is in Newton, so it will be 0.06 I 0.075 J plus 0 K meter. So I have my force and position vector written in Cartesian vector form, and if I have that, then all I have to do is to find the cross product. So if I go back to my problem, all right, I'm going to take this off, but I'm going to rewrite before I go these units. R is 0.06 I plus 0.075 J plus 0 K is my R. Similarly, my F, which is the force, equal to 0 I minus 200 cosine 30 degree J plus 200 cosine 60 degree K. So I got all this stuff, and all that is left for me to do is to find R cross F. All right? I want to make sure you understand it has to be R cross F, not F cross R. So we have our force vector, we have our position vector, and we are crossing them, and R cross F should give a moment vector, which is moment of this force about point A. All right? Since it is in 3D, instead of doing all the details, I'm going to put this into the form that I talked about. Here comes my R, which is the x component 0.06, that's my unit vector I. J, 0.075. K, I have a 0. So this row belongs to the components of position vector. The next row belongs to the components of force vector, which in this case is 0, negative 200 cosine 30. Remember, this is just one component of y, and the last one component, I'm going to squeeze that in here, 200 cosine 60 degree, and that's my determinant form. Now, I'm not going to spend time expanding this because you should know this. If you did not, look up another lecture where I have explained this one. And all I have to do is to evaluate. And if I evaluate, R cross F is my moment vector about point B, and that happens to be 7.5 I minus 6J minus 10.4 K. This is the answer, and the answer is not complete without units, and the units in this case is Newton meter. So moment of a force about this point has been calculated. The first step, define your position vector and the force vector in Cartesian vector format, and then simply apply the math or vector algebra, and you should get the answer. All right? That completes our discussion on three-dimensional moment calculation as well as on vector product. And now we will move on. Thank you.